Hey class, today we're going to take a look at a couple of problems and work through the proofs for them. The Basel problem, which is written behind me, and the Collatz problem. So the Basel problem was solved by Leonhard Euler, this Swiss mathematician who spent a fair amount of his time in Russia and Prussia, which would eventually become Germany. And at age 27, he was able to come up with an argument that whose structure would later become formalized as a proof once Weierstrass came along and proved certain methods were valid. But he was able to demonstrate it, just like we were with numerical methods, where if you're at a for loop, then you could just add up these terms. He was able to just will his way to increase the precision on this, and then at the age of 27, after he'd been hammering away at it for a few years, increasing the precision several orders, he was able to get this insight that allowed him to make the argument that we'll go over here in just a few minutes, and come up with this equivalence. If you look at it, just adding up 1 plus a quarter plus a ninth plus a 16th plus a 25th, it doesn't seem all that obvious that it should add up to a number that to pi squared over 6, and at least not to me. If it's obvious to you, then you are a better mathematician than Euler, who took several years to come to the solution. But whenever he did eventually solve it, the math community named the problem in honor of his hometown. The guy from Basel that was able to solve this problem, and it's I like to look at the timeline in addition to the proof. So the proof itself is really interesting, but the timeline shows just the amount of persistence that it takes even great mathematicians to come up with a solution to some of these problems. So we look at it, we see the solution, and at least whenever I was an undergraduate, I was coming across these things and thinking, how am I supposed to come up with that? Someone was able to come up with it, and then I had a lot of really smart friends, and I guess they had just gotten to studying this stuff before I did, and so there was always at least one person around me that was already familiar with what it took for some of these remarkable results. And I remember just there's a fair amount of frustration as you're going through it. Like, well, okay, so other people are able to do it, but that doesn't really apply to me, right? Because I don't see it. But even so, it's important to keep in mind that every proof or every result of any significance, it took the math community a fair amount of time to recognize that whatever it is that you're trying to prove was even a problem to begin with, and then it took some additional amount of time, some non-zero amount of time, to come up with a solution for it. So you see the results presented to you in whatever class. You see the results presented to you in whatever book, or whatever video, or however you're coming across it, and it can seem like it can feel as though it's instantaneous, that others are getting this stuff basically as soon as they see it, and that's never the case. It always takes a fair amount of time and effort in order to come up with any result of significance. So if you struggle, or if something doesn't seem all that intuitive whenever you first encounter it, that is the way of it. That's kind of how it goes. It's certainly no indication as to whether or not you'll be able to make contributions yourself. The important thing is to just kind of work through that, and if you happen to be like me and you feel a little um, skeptical about your ability to make contributions early on, well, um, that's that's kind of how it goes. Okay, so Basel problem. How do we come up with this actual answer? Okay, so let's talk about just polynomials in general real quick. Okay, so this binomial, we can assume that a and b are some constants, and then x is the variable. And when it's in this form, we can see that it's the product of these roots. So this polynomial, or this binomial, will have uh, a root at a. So when x is equal to a, this will be 0, and when x is equal to b, this will be 0. And then we can multiply it out, and we can get something that's a little more familiar. So so we'll get something of that form, right? X squared, and then minus bx minus ax. We can simplify this to and then over here ab. Okay, so another way to look at this without changing the roots necessarily is to scale this down. So we could just divide it by AB. So we have a polynomial that is in some sense related to this original one. It has zeros at the same values, but the actual f of x value, or the actual y value, however you want to say it, is a little bit different. So instead of peaking, or having this first term of AB, it has a first term of 1. It's But they're still very similar polynomials. It's going to have the inflections in all the same places. It's just a scaled down version. So you can think of them as, in some sense, being in an equivalence class with each other. Okay, so this form would be written slightly different from this one. And so, if you're so inclined, instead of writing it in this form, if you want, then you can just divide through whatever this coefficient is, and you haven't changed the point at which this value is 0. You've just written it in a different form, but it's still the same polynomial. It's just that scaled down version. So that now, whenever you multiply the first terms, you get 1, and then the mixed one. Is scaled, and then the highest degree term is also scaled down. But it's still 0 at all the same points, and that's kind of what I want to emphasize. So, okay, so now something that a pattern that you'll notice whenever you start getting into proofs, and we talked about the bag of tricks that you'll develop for dealing with these proofs. One of them is power series expansions, and then another one, which I'll have to come up with at some point, is just all of the trig identities. But I don't have any good examples for that, but sometimes it's helpful to have the trig identities. We won't jump into those today, but we will use the power series expansion and then this trick, right? So converting a polynomial that has zeros at a, b, and so forth into one of this form. Okay, so actually, let's hold off on doing the power series expansion. We'll do the factorization first. Okay, so something that Euler proposed was, and we mentioned that there was this time when we didn't really consider special functions or anything else. There was this insistence that polynomials could really be used to represent basically anything. And so sine and cosine, before we had I guess we did have the power series expansion at that point. But Euler saw it and he thought, okay, well, if I have this function and I know all of the roots and and it can be represented as a polynomial, then I can write it in terms of the factorization of its roots. And so it hadn't been formally proved yet, this concept, but he had this insight and he would use it on this problem. And so he looked at sine of x and he saw that it could be written in a couple of different ways. So one of them is the Taylor series expansion. So so it's in this form, right? There's infinite sum where we alternate every term as whether it's odd or even. The first one, or sorry, whether it's negative or positive. And then we take all of the odd powers of x and we divide it by the factorial of the same. Right, so x minus x cubed over 3 factorial plus x to the 5 over 5 factorial. And then simply by knowing that it had roots at all of the multiples of pi. So sine of 0 is 0, sine of pi is 0, sine of 2 pi is 0, and so forth. All of the positive ones and all of the negative ones. Then he asserted, without this formalized proof, but he asserted that, well, I have something that we're already writing as a polynomial, and I know all of the roots, so can't I just write it as a product of all of these roots, just like we were doing before? And so if he did that, then he could write it like this. But if he manipulated it in the same way we said, then he could rewrite it by just dividing the terms by this, right? So 1 minus x over pi, 1 plus x over pi, and so forth. Okay, well, this has this nice cancellation property, so that if you multiply by the positive and negative versions, you get x minus y times x plus y is equal to x squared minus y squared. Right? So in this case, x is 1 and y is x over pi, x over 2 pi, and x over 3 pi, and so forth. And so now we have something where he has this sequence. He's created this this product, this infinite product, where we have this x floating out front, and then we have this thing with these coefficients where we have all of these x squared terms, but the zeros are at when x squared is equal to the square of the natural numbers times pi, right? That's where all of these zeros are. So whenever x is pi, whenever x, or plus or minus pi, plus or minus 2 pi, plus or minus 3 pi, and so forth. But in the denominator, right? So we have this pi squared there, which is doing whatever, but it's multiplied by all of the natural number squared. So it's starting to look a little bit like that sequence that we were looking at earlier, 1 over n squared, right? So this is 1 over 1 squared, 1 over 2 squared, 1 over 3 squared. And so you can imagine him working through this problem a little bit, thinking, okay, well, I have something that it's known, right? Sine of x is pretty well known, and we have these manipulations that we can use for it. But it's still, there's still some work to be done. What does he have to do to get there the rest of the way? Okay, so he has these equivalences, right? And so he has this over here. But he has all of these x squared terms over here, and there's this one lone x term. He could greatly simplify this problem by just pulling this over to the left-hand side, right? And so in order to do that, he has to do it here, well, really everywhere, right? Every version of this is going to have that x divided through. And so if he does that, then he gets something of this form. Right? So, okay, so now it's a little bit simpler. He doesn't have that x term, causing problems in the front. And now he has something that he's kind of eyeing. Well, okay, so he has all of these 1 minus x squared divided by something pi squared, right? Divided by the term that he's interested in, that 1 over n squared term, times pi squared. And grouping like terms, so we're taught whenever we're solving these problems in middle school that if you have coefficients on the left-hand side and coefficients on the right-hand side, then you can group these coefficients by whatever they're multiplying. So the coefficient of x to the sixth on the left-hand side has to equal the coefficient of x to the sixth on the right-hand side if the statements are equal. And in this case, the x squared coefficients would all have to equal this x squared thing. So how does he pull them out? How does he do that? And so at some point you can imagine like him just working through this problem, feeling the hunt. He's getting closer, and he thinks, okay, well, what if I just group these terms? So if he multiplies this out, if he does the absurd thing and multiplies this infinite product out, then applying FOIL, right, first, outer, inner, last, all of the first terms are 1. So he'll get something of the form 1, and then the next one will be, if he then takes exactly, so we're now going to create this by choosing how many of each of the second terms we include in our product. So if we do the thing where we go and we take the second term, or the second variable or whatever, in this first factor, and then we take all of the first terms from there, then we'll get minus x squared over pi squared. And then if we take exactly one second term and we do it from this second factor, then we'll get minus x squared over 4 pi squared. Same trick with the third factor. If we take 2, so then we would get something of the form and so you can see that it's starting to play out. We're getting something over here where we have 1 corresponds to 1. X squared, negative x squared over 3 factorial corresponds to all of these negative x squared over something pi squared terms. There's an x to the 4, just as expected, and so on and so forth. So you can actually group all of these like terms. Well, it becomes increasingly painful to kind of write the shorthand for each of these other terms, where you're taking 2 of these later terms, and then 3, and then 4, and so forth. Luckily, he didn't care. He had exactly what he was looking for. So now he's found a way to extract those terms that he cared about from the rest of the problem. So you can now, just grouping like terms and realizing that all of the x squared terms are going to have as coefficients these 1 over n squared terms that he was curious about in the first place. And so we can rewrite it and so he can rewrite his problem here, right? And so these are the terms he cares about. This is a multiple in every one of those terms. This is a factor, this negative x squared over pi squared in every one of those terms. But you can factor that out, and you get a series, a summation of 1 over n squared times that. Well, if it's a factor in every one of those terms, you can just factor it out from the series. So it moves outside of the sum. Okay. And then we can just move it to the other side of the problem. So the negative x squareds will cancel out. And we'll end up with and then 3 factorial is just 6, and that returns us to our desired result. And so yeah, he went through and he verified it numerically. He computed this to several digits. He verified that that sum was corresponding to it. And while he had taken a few liberties, a few leaps during this proof, he convinced himself that this is absolutely what it's converging to, and it's remarkable. So. That's kind of the way it goes sometimes. You're not sure. You're breaking new ground. You know that if something is true, then your result will be correct. You're pretty sure that you're working under the correct assumption, and then you go with what you've got, and then later on, Weierstrass came along. He's like, you can actually use that. The product of the zeros, the factorization, that's completely valid. But he already knew from numerical methods, or from pen and paper, that what he was doing was right, and he'd convinced himself. And really, that's kind of what you're going for whenever you're trying to prove anything, is just to convince yourself. So if you get to the end of the problem, you're asking, okay, well, have I done it? Has this actually been proven? Then probably not. If you haven't convinced yourself, then you probably still have a little bit more work to do. And that's fine. That's kind of the learning curve. But if you have convinced yourself, more than just like going through the motions and like, okay, well, I think I've applied induction correctly. If your arguments are sufficient to convince yourself, and you have other evidence to suggest that what you're trying to show is true, then you can feel confident that you're at least on the right track. Okay, so then the other problem that I wanted to consider was the Collatz problem. So that one is a series. It's a recursive series, but it's defined in terms of these branching operations. So you behave differently for the odd numbered values than you would from the even number values. And so we'll manipulate that a little bit, and then we'll look at a way to actually prove that. So. Okay, so this problem, you divide the so you obtain the next term in the sequence by dividing by 2 if the numbers are even, or multiplying by 3 and adding 1 if the number is odd. And so this so multiplying any odd number by 3 is going to give you an odd number. So adding 1 makes it even. So you'll always follow an even term with an odd term with an even one, and you'll end up dividing it by 2. And so there's this question, and it seems reasonable that we would expect that eventually you will find a value that will allow you to divide this all the way down to 1. So eventually one of these terms will be some power of 2, and then we'll just follow these right shift operations, dividing by 2, all the way back to the value 1. And then the sequence is halted then, because so 1 is an odd number. So you would follow this term, or this rule. You would multiply by 3, so you'd get 3. Add 1, you'd get 4. And then you would have an even number. Divide by 2, you get 2. Divide by 2, you get 1. And you end up with this cycle. Right? And so we've established that there is the possibility of having a cycle. And so the question is that it? Is that 1, 2, 4, or 4, 2, 1, 4 cycle the only loop in all of the positive integers? Or is there another one? Is there some other value where it'll just bounce around in a circle? Or does every other number converge down to 1? And so that's the whole question. And because it deals with these branches, it makes it a little bit confusing how we would go about figuring that out. So one way to view the problem is to reinterpret the question. So if we start with 1, is it possible to go up to reach every other positive integer using the inverted rule? So this is how we would, in theory, fall back down to 1, but could we go in the other direction? And so the first step toward doing that is to modify this sequence a little bit and just join these steps, right? So this is always going to give you an even number, so let's merge that into a single step, and we'll just divide by 2. And now there's a question of whether or not whenever we apply the rule for odd numbers, whether the next term is odd or whether it's even. Okay, so we can define this other sequence. Okay, so this is more of a relation than it is a function. So this is at least deterministic. You apply one or the other. But in this case, if we write it in this format, we're actually choosing multiple values for every input. So we have some term b sub n, and the output is going to be one of 2 possible values, and it's branch points essentially. So this is essentially constructing a tree, and so one child is going to be twice the input value, twice the parent's value, and the other child will be 2 divided by 3 times the previous value plus 1. And so you can see that these are just inversions of the previous terms, right? So instead of dividing by 2, we're multiplying by 2, and instead of and instead of doing 3 times the previous term plus 1, we're inverting the operation, so it's 2 divided by that. Let's see if that's correct. I may have miswritten it. It might be that. Right? I said it's of the same form. We didn't just divide, that we multiplied instead of dividing. Let's see. We'll see. The terms should be the same, but they should be in reverse. So let's pick a few. Right. So for this one, we'll see. These operations should be inverted, so we should be able to get to the parent by applying these rules, and we should be able to generate children by applying these rules. And if that's not the case, then I have messed up the sequence that I was constructing. Okay, so we start with 1, and 1 child is, if we apply this rule, it's 2. If we apply it again, we get 4. And if we apply it again, then we get 8. Okay. Okay. So then how would we get 4 by applying this rule? Okay, so the correct inversion we just solved for it, right? So this is an plus 1, and we get there by applying this rule, 3an plus 1 divided by 2. So then you bring the 2 over, you get 2 times an plus 1 is equal to 3an plus 1. 2 times an plus 1 minus 1 is equal to 3an, and then 2 times an plus 1 minus 1 all divided by 3 is equal to an. So let's rewrite our rule. So now we know how to generate the other child, right? The right child. So if we apply that to 1, we get 2 times 1 minus 1 is 0, divided by 3 is 0. But we don't actually want 0. We're only including the natural numbers, so nothing smaller than 1. So basically, we only want terms that could possibly appear in the Collatz series, and 0 is not one of them. Okay, so we do the same thing to 2. We get 2 times 2 is 4, minus 1 is 3, divided by 3 is 1. Okay, so that's correct, but that generates a loop. We do the same thing to 4. We get 8, 7 divided by 3. And we see that it violates our insistence that our terms be natural numbers. So now we see that it's possible that we can exclude right children. So when we multiply by 2, we're always going to get something that is, again, a whole number. But whenever we do this, at least 2/3 of the time, we would expect to come across something that isn't divisible by 3. And so there's going to be a lot of dead branches to the right children. And we were kind of already expecting something not terribly interesting because 1, 2, and 4 create this cycle for the Collatz series. So really, everything of interest in terms of what is actually reachable by our sequence. So all of the numbers that can see 1 in the Collatz series, or all of the numbers that 1 can in some sense see or reach in our reverse Collatz series, would all be, with the exclusion of these 3, they would all be accessible by 8. So really, 8 is in some sense the natural root for the tree generated by this sequence. So let's do a couple of those terms, and then we'll jump over and look at the proof. Okay, so the left child is always multiplication by 2. So we see that we're going to have this line of powers of 2 just along the left side of our tree. And then everything to the right of it will be some descendant of that power of 2. So the Collatz series would have to pass through that particular power of 2, and then it'll just be right shifted. It'll be divided all the way up the tree to get back to 1. Okay, so 2 times 8 is 16, minus 1 is 15, divided by 3 is 5. If we try and apply it again, so we can multiply 5 by 2, and we get 10. So 10 is a number that converges. And 5, if we apply this rule, we get 10, minus 1 is 9, divided by 3 is 3, so forth. If we try and apply it to this, we get 32, minus 1 is 31, divided by 3 is 10 and a third, or 31 over 3. So that's a dead branch. And once you reach a value that is a rational number, but not an integer, it's dead the rest of the way. You can never recover that branch. Multiplying by 2 will not make it more divisible by 3, and then doing this operation never quite recovers it. So it's forever lost to you whenever you do that. So you have to stick to just the integers. But you can see that it's starting to construct this, and at least some of the numbers will be accessible. And so then the question is, okay, well, we can invert it, and we can kind of see how you can reach certainly an infinite number of terms this way. If nothing else, the powers of 2 are all accessible to you. So then, how do we get there? Well, we can kind of see that the powers of 2 are going to be at least a little influential, because they are the ancestors of all of these other branches. Everything is branching off of one of these powers of 2. So is there some way we could view that? It seems like it's going to be written by 1, 2, and 3, right? So those are the terms, the constants that all appear here. We're adding 1, we're dividing by 2, we're multiplying by 3, and we have this influence that we have this binary tree where these decisions are made. It's a left or a right decision, and powers of 2. So one possible way of looking at this problem is to look at it in binary. So what do we need in order to do that? Okay, so last time we discussed multiplication by 2 is a left shift operation, and division by 2 is a right shift operation for binary. And then adding 1 is just adding the least significant bit, and then you have those carry bits as well. So then what is multiplication by 3? What does that look like? Well, it may surprise you to learn, but 3 is equal to 2 plus 1. So the 3 is equal to 2 plus 1 times our previous term. Right, so that's how we perform that operation. So then if we write this in some binary expansion, then it's going to look a little bit like a polynomial, but all of the coefficients will either be 0 or 1, and then the x to the power n or whatever is going to be 2 raised to some power, right? So just like when we write numbers in decimal, we're writing some coefficient times 10 to some power. So we have the millions place, the 100,000s place, the 10,000s place, the thousands place, and so on and so forth. Well, binary's basically the same thing. So you have your base raised to some power, and then a coefficient that ranges between 0 and 1 less than whatever your base is. So in decimal, all our numbers are 0 to 9. In binary, all of our numbers are 0 to 1, which is 0 or 1. So so we have our coefficients times our powers of 2, right? So this is our expansion, and it looks just like that. So then 3 times this number, well, so 2 times this number is going to just be a shift. So if we do that, then we have all of the same coefficients, but the power of 2 is incremented. So it's, instead of our most significant coefficient, ck, times 2 to the k, it's going to be that same value, ck times 2 to the k plus 1. And the same is true all the way down the line. So instead of c0 times 2 to the 0, or times 1, basically, then c0 times 2 to the 1, or 2. And so the exact same coefficients in the exact same order, but the power of 2 that they're associated with has been increased. Well, okay, if this is a sub n, and this is 2 times a sub n, and 3 a sub n is is 2 plus 1, right? Then 3 is going to be adding these terms together. Okay, so then do we group by coefficients or do we group by powers of 2? Well, we're looking at binary expansion, so that we group by powers of 2. And we end up with okay, so there's only 1 2 to the k plus 1 term. There's 2 2 to the k terms. C sub k and C sub k minus 1. So we add those together. And then all the way down the line, right? So C1 plus C0 times 2 to the 1 plus C0 times 2 to the 0. Right? So we get something of this form. So by multiplying by 3, we add together all of these neighboring coefficients, and we group them by the power of 2 in the binary expansion. And we get this representation. So now we can represent multiplying by 3. Adding 1 is just adding 1 to this, right? So the it's the exact same thing, but you tack on a 1 at the end, right? Or some additional 2 to 0, right? So it could be C0 plus 1 on that. Okay. And then this division by 2, if we apply it, or if we keep it as a separate step, then that's a different thing. Would just be shifting to the right, whenever it applies. Okay, so we know that this rule only gets applied if it's odd, right? So in that case, C0 is 1, and 1 plus 1 is 2, so there's going to be this carry bit, and we're always going to end up with this even value at the end. So, okay, we kind of have what we need to get started on this problem. So let's jump over to the notes, and then we'll finish off and be done for the day. Okay, so now we have our series, and so what if we just reconsidered it and constructed a different series that's very similar? So instead of dividing by 2 whenever it's even, to get it back down to something where we add 1 and then it generates this different term, what if instead we only ever expanded it, we only ever grew it, multiplying the previous term by 3, and then the equivalent of adding 1 is we just add 1 to whatever the least significant bit is, and so that's what this sigma of a sub n minus 1, right? Where this sigma of a sub I is equal to the largest value k, such that dividing out that power of 2 to the k is still a whole number. Or you could say the same thing. The equivalent statement is sigma a sub I represents the smallest non-zero coefficient in the binary expansion of a sub I. Okay, so let's call this our sweeper term. Right? So it goes through and it looks at the binary expansion, and it takes whatever that trailing bit is, and it adds 1 at that place, at the least significant uh, non-zero coefficient, and it increments it by 1 so that it promotes it a little bit. It increases the value. So this is the same as 3 plus 1, but we're now moving that 1. It's plus 1, but 1 shifted to the left by k. Right. Okay. So we're applying our knowledge of computer science here. Okay, so this is what I was showing, the polynomial representation, right? Using base 2 expansion of a series. Right? So you have some value n, and this is how you would represent it in binary. The 1s, the 2s, the 4s, and so on, up to the 2 to the k term. Okay, so now let's define this other series, and we'll show how it relates in a little bit, of b sub n, where the terms, where it's 4 times the previous term. So then it's 4 times 4, the term, or the term n minus 2 terms ago, or whatever, right? So if you go back 2 terms, then it's 4 times 4. If you go back 3 times, it's 4 times 4 times 4, and so on. And so then b sub n is 4 to the n times whatever your original value was, b sub 0. Okay, so the series, where we're just ever growing it, right? So 3 times a sub n plus our sweeper term is given by this. So if we start with the a sub 0 equals 1, then we're growing it 3 times 1 plus that least significant bit. Well, it's 1. Right? Sorry. That's 1. So then 3. This turns into 3 plus 1, which is 4, which is equal to our b sub 1 term, right? So if we start out with 1 here, then these agree. B sub 1 is equal to a sub 1. A sub 2 is equal to 3 times our previous term plus our sweeper function. Right? So over here, that was 2 to the 2. So the least significant bit is 2 to the 2. So 3 times 4 plus 2 to the 2 is 12 plus 4 equals 16. Well, that's 4 squared, and that agrees with the second term in our B series. And so this holds true. So if we start with 1 and we use our growth function with the sweeper function as defined, then we end up with this series, which is always 4 to the n, and that's b sub n. Okay, so that's essentially the fastest that a sub n series can grow, and we'll see that in a little bit. And so at its peak, it's growing at a rate of 4 to the n, which is exactly that second series that we have. Okay, so we know that it's achievable that it can equal 4 to the n, and it can't go any faster. So why are we looking at it? Why have we defined this really complicated way of looking at something that's basically 4 to the n? Well, because this shows that the way that we're looking at this problem by tacking on that, an addition by the least significant power of 2 from the previous term, is kind of the upper bound of the series that we're looking at. So let's continue to massage the problem a little bit and see what we can do. And I have an extra parent in there. Okay. All right. Oh, whatever. Okay. So our sweeper term is maximal whenever a sub 0 is power of 2. And this allows the sequence to grow at its maximal rate of 4 to the n. The binary representation of the iteration step is given by this, which we were just looking at, right? So you multiply from the previous term, c sub k term now represents 2 to the k plus 1 and then you're grouping the neighbors and so on and so forth, and you end up with that trailing term, and our sweeper term is exactly equal to that. Right? So you can see it's another way of looking at the exact same thing. And so where C sub k is the non-zero coefficient of the largest power of 2, the most significant bit, and C sub j is the least significant bit. Okay, so then in the case of, or the least significant set bit, the least significant one that has a value of 1. Okay, so in this case our sequence a sub n minus 1 is equal to a power of 2, and the right hand side simplifies a little bit. So then we have our most significant bit and our least significant bit are the same thing. So it's multiplication by 3 is multiplication by 2 plus multiplication by 1, right? So we get this, and then we have our sweeper term here, which is the least significant set bit, which happens to be the only significant set bit. And so then we see that this is in fact 2 to the k plus 2, right? Where k was the power of 2 for our term. And that's in the case whenever our terms are a power of 2. Okay, so we'll approach this via a proof by contradiction. And let's see. Okay, so to arrive at a contradiction, let's assume that the terms a sub n don't converge to a power of 2. Okay, so we're multiplying by 3, we're adding some value that's less than our previous value because otherwise we would be adding this, right? If it's not less than the previous value, then it's the case where we're adding a term that's equal to the most significant set bit, right? So then our series may be represented in binary using this sequence, right? So this is the same as before. This is the binary representation of 3 times the previous term, and then this is our sweeper function, and then this series is bounded above by the series where we choose. So if it doesn't converge to a power of 2, then this sweeper term will be maximal at whatever the bit is just below the most significant set bit. Right? So that's all we're saying here. And so, and then that in itself, right, yeah, so that's equal to half the value of the most significant set bit. So then our terms would be bounded above. Instead of going with the least significant bit, we can bound it above by choosing the one next to the most significant bit. Okay? And that's in the case that, and again, we're proving by contradiction, right? So we're going to show that this statement will lead to a contradiction. So, so hang in there. Okay, so in this series is in turn bounded by the series where we add 1.5 of the total value, right? So we have this term where we're now choosing the second most significant bit, or half the value of the most significant set bit. And we say, okay, well that one is included, so if you do a right shift operation, then this is right here. And so we have 3 times the previous value, and then we have 1/2 times the previous value, and this is larger than, so here we're choosing the smallest term, right, the way that we've originally constructed it, or the way our sweeper term is defined. And then here we've chosen something that's even bigger than this, or that's at least as big as this. And we say, okay, well that is included if you do 3.5 times, and then you add all this other junk on top of it, that's even bigger. So we've constructed in such a fashion that we have something that is definitely larger than the way we're defining a sub n. Okay, So now we'll call this series A bar sub n. So the A bar series in terms of our A bar series. So these terms are constructed by looking at the previous term. You multiply by 3, and then you add 1/2 of whatever that previous term is. Okay, well that simplifies to just 3.5 times that previous term. If you apply it repeatedly, then that's 3.5 to the n times whatever the first term in your series is. Okay, but if you look at this in the limiting case, then 3.5 to the n times a sub 0 divided by our sequence 4 to the n, well, that's equal to this. You just set the a sub 0, the a bar sub 0 aside, and you get 3.5 over 4 to the n. Well, anything that's smaller than 1 to the nth power is going to tend towards 0 as n goes to infinity, in the same way that anything that's larger than 1 raised to the n would go off to infinity. So we have this series which goes to 0, and this is the case whenever the series in the denominator is strictly larger than the one in the numerator, which is obvious, right? Like you really don't have to look at it all that much, but we state it for formality. So then our series B sub n definitely outgrows A sub n, and we know that it essentially chases it down. Right? But we chose the terms in A bar such that they're larger than A sub n. Right? So how can this be that our series is outgrown by a series which it is bounding below? And we've already shown that this at least grows by 4 to the n. Right? So what gives? We have a contradiction here. And the thing that gives is that this series, the way we've constructed it, it isn't a valid representation of the original series A sub n. It's not a valid bounding for it. And that's because it has to converge to a power of 2. We've constructed a series, and it definitely outpaces 4 to the n, or at least grows as fast. And whenever it hits its stride, it's growing at 4 to the n. And the way it does that is by converging to a power of 2. So our restriction that it never converges is demonstrated to be false or inviolable by this limit. If we hold to that, if we insist that it never converges to a power of 2, then it can never achieve its full pace of growing at a rate of 4 to the n, and we have a contradiction. So that means that the 3 a sub n plus 1, or plus our sweeper term, eventually converges to a power of 2. Okay, well, yeah, that's basically what we're trying to show, but we have to demonstrate why that was why we were trying to show it, and relate it back to the Collatz series now. Okay, so consider this third sequence, C sub n, so that instead of adding a sweeper term, we divide by 2 until we reach an odd number, basically, until that smallest term is 1, our sweeper term is 1. Okay, so then now we have 3 times the previous term plus 1 for odd numbers, and divided by 2 for even numbers. And you divide again and again and again until you get an odd number, right? Which is what we're doing with Collatz. So we haven't changed the convergence behavior. This is still the same thing with our sweeper function, but instead of using a sweeper function where we're using that least significant set bit, we shift right until that least significant set bit is 1, until it's the least significant bit in the binary representation. Okay. So then it's the same sequence. It converges in the same number of operations, except we have this additional work of k divisions, where k is that least significant bit. So it's the degree of evenness or whatever. So 2 to the k equals a sub n 0, where n naught was the point of convergence to a power of 2, or another way of looking at it, it's the first such value that with our initial value times 3.5 to that value n naught is outgrown by 4 to the n naught times 1, right? So we start off some point ahead, and then eventually it's outgrown by 4 to the n. And so that point of contradiction that we had constructed, that actually creates this upper bound for how long it can possibly take before the series has to converge, before the Collatz series has to converge to 1. And so this sequence, C sub n, represents the terms of the Collatz series, and we can compute in 0, that point where it's forced to converge, by thinking about the series B sub n, which is just 4 to the n, as forcing our terms A sub n to a power of 2. We can put a bound on how long this will take by returning to the contradiction criteria. And so it'll converge at or before the value n, such that the numerator is overtaken by the denominator. Right. And so okay, and so we just look at that again. Okay, well, we move a0 to the right hand side, and now we have this ratio, and they're both raised to the n, so we can put that outside the fraction. Now we can take the log of both sides, and then we get n times the log of this is less than or equal to the log of that, and then we pull this over to the right hand side, and so we have that n, so that it'll converge sometime less than this ratio, sometime before n at this ratio, and then plus those k divisions. So whatever this n is gives a limit to that 4 to the n, and then you would add 4 to the n, that's 2 to the I think it's 2 to the 2n, and then yeah, so then 2n division operations. So this plus 2 to the n, or sorry, this plus 2n division operations. So something like 3n of this ratio will give you an upper bound for how long it takes to converge. Okay, so next time we will do additional proofs. If I don't have a homework assigned to you by midnight, then you're off the hook this week. Okay, I'll talk to you all on Thursday.